Okay. Hi, everyone. Thank you for coming. Sorry about the technical difficulties. Took us a few minutes longer to get started. My name's Chris Laver, Chief Data Scientist at Chisel AI. I'm going to be talking to you today about one of my very favorite papers, Adaptive Computation Time. It's from a scientist at DeepMind named Alex Graves, who's done a lot of other interesting work as well. Highly recommend, look him up. I normally start these talks with a joke, and it's normally the same joke. Unfortunately, it's the very same joke I used when I spoke in this forum last year, so I'm not going to repeat myself. Instead, I'm going to start with a thought, and that's that I really enjoy the AISC sessions, particularly looking at papers that are a little bit past. One of the things it lets us do is pause and consider. It's a chance to think about papers that aren't cutting edge, aren't yesterday, but still have something important to offer. And I say pause and consider carefully because I think that could have been an alternate title for this paper, is pause and consider. So I'll start with considering the following stream of tokens. The President of the United States of America is Donald J. Trump. There's zero judgments here, just a stream of characters. But not every token in that stream carries the same amount of information. Even two tokens that are syntactically the same. Of the President of the United States of. That word of. This first one could be anything. That sentence could go in a lot of different directions. But after we've seen the tokens United and States, and we see the token of, there's very little information there. The word America is almost always going to follow that. It would be very rare for America not to follow that. And yet, whenever we use a standard RNN model, we're applying the exact same amount of computation, the exact same amount of time spent pausing and considering on every single token. It's not only NLP, anything that you would apply an RNN to, a time series, for example. I've marked two spots on this time series, what it is, unimportant, A and B. And I would argue that if I were looking at this time series, if you pointed me at point B, I would look at it and say, okay, it's kind of descending, it doesn't look too irregular. If you direct me at point A, we're right in the middle of a big spike. I have no idea what this represents, but I would want to know more. I would want to stop and think about this more deeply than if we were just in a normal steady state type of activity. Now, a standard RNN, this is just the unrolled view, taken from an excellent primer on LSTMs, by the way. You have inputs, X. You have a sequence of them, X0, X1, X2, all the way to the end of the sequence. You have whatever your RNN model you've chosen to go with, carrying state. That could be something as simple as just carry state forward from the last iteration of a standard neuron. That could be something a little bit more interesting, like an LSTM or a GRU. Doesn't really matter for this unrolled view. And then we have outputs, which are, in this case, confusingly labeled H instead of the standard Y. But every step, every input, we're updating the state based on the input and whatever we saw previously, and we're outputting something, we're emitting. Now, these RNNs, they work really well on sequences to do NLP tasks, next character, next word prediction. Until some of the recent transformer work, these were pretty much the only game in town for how we dealt with sequences of tokens. But some sequences are just plain hard. Not all sequences are created equal. Pronoun resolution, Jeremy picked up Matthew from work, then he drove them to the park. A human reading this is probably going to conclude that he corresponds to Jeremy, could correspond to Matthew, but probably doesn't. I think we've all seen Winograd schemas. In this case, the city councilman refused the demonstrators a permit because they, this word here, feared or advocated. Seems like a small difference, but if you change which words you're inserting there and give this to a person to read, the connected tokens in this sentence change. Because they feared violence, well, you'd be talking about the city councilman who feared violence. If you chose the token advocated instead, well, clearly to a human reading it, that's the demonstrators advocated violence. Prepositional phrase attachment. The man saw the boy on the hill with the telescope. Well, with the telescope, is that the man who was using the telescope saw the boy on the hill? Was the boy on the hill carrying a telescope out for some late night astronomy? I don't know, but this sequence is much, much harder than sort of a standard sentence, a standard sequence you might see in written prose. So how might we let an RNN stop on some of these difficult examples, some of these difficult tokens, and consider? Well, we could try a really coarse tool, something that requires a lot of human input, and say, well, in this sentence, we have to resolve this pronoun. We could just repeat the pronoun a bunch of times and let it ponder for a while, let it spin and update its state internally. That's really awkward to do with a standard RNN. First of all, you're emitting several times. Do you emit at these repeated states? How does the network know how to deal with those repeated emissions? Are we adding extra flags to say when it was a repeat? Are we adding extra flags to say this is something you should be considering? How do we know how many times we need to repeat these tokens to get the point, to give it a long enough time to pause and consider? That's where the paper comes in. Okay, enough with the preamble. So Adaptive Computation Times from Alex Graves, DeepMind in 2016, one of my very favorite papers. It proposes a mechanism to pause and consider spending additional computation on tokens in a sequence that have more information, that deserve extra computation. That additional computation budget is allocated dynamically and adaptively. I don't want to have to be the expert saying which tokens are important. That doesn't scale, and that just sounds awful. I don't want to do that. We do have to add an additional neuron to the network, to the recurrent unit, that gives instruction to the network about, do I proceed, do I stop, do I consider longer? And before we dive into details, I wanted to start with some of the reasons you might or might not choose to use the technique outlined in this paper. Advantages is you get to spend more time on tokens with high information. That's adaptively determined. There's no manual input to determine when that happens. And it's a generic technique. I'm going to show you this applies to any of the standard types of RNN. Now, there are some disadvantages. The first being that RNNs, LSTMs being the canonical example, they're already expensive. Why would we want to add more computation to a technique that's already super expensive? And the second disadvantage is reiterating the first point. They're already really expensive. Why are we adding more compute? And there is a third disadvantage, which I consider more annoying than anything else, which is that we have to add a hyperparameter that it's difficult to set in a principled manner. We already have enough hyperparameters. We don't want to expand the search space any larger, except we're going to because I'm the one up here talking. So just as a reminder, this is sort of the unrolled standard RNN view. At the bottom, we have this series of tokens, X. T represents time. We proceed through time. These S's, the small S's, represent the internal state of whatever RNN method you're choosing to use. These script S's represent state transitions. This is how we abstract away from any particular model of RNN. I'm just saying that we have these state transitions that will take us from the previous state to the new state based on whatever the input token we're looking at is. And that could be commonly LSTM, GRU. These are parameterized with whatever parameters are necessary to compute your RNN flavor of choice. And then we have output. At every time step, a standard RNN is going to create an output vector, one emission. The parameters that are going to go into this are the weight vector, or the weight matrix that applies to the inputs, WX. Script S, the state transition, is parameterized in some way. Then we have the output weight matrix, WY, that transforms the state into the output. There are also some activation functions going on of your choice. We're not going to cover those. They're not important to the technique. Now, this is what ACT, Adaptive Computation Time, looks like. And there's a lot going on here. I'm just going to pause for 1 second. But this diagram is very similar to what we saw on the previous page. We still have these dotted lines that separate time. This is still time step t minus 1 and time step t. At the bottom, you can see xt minus 1 and xt. We still have the same inputs coming in. And at the top, yt minus 1 and yt, we still have outputs going out. All that we've done is changed the internals of how we're computing those same input and output vectors. Now, we've pretty significantly changed them, so we're going to go through how we did that. But you'll notice that all the parameters are, for the most part, the same. We still have the wx weight matrices that work on the inputs. We still have the wy weight matrices that transform state into output. We've added this wh, which I'll describe in a few minutes. But everything else remains the same. And this is how it does it. So we're going to talk through one of these columns at a time. Each of these columns represents intermediate steps that are happening inside a single time step. We've added depth to this RNN. So every time that we're walking up one of these columns, we're staying on the same token. We're pausing and considering without advancing time. And we're going to take the states up the center first. So you can see that we have, oh, what am I stepping on? It's okay. So you can see we have states up the center. We have state at time t, step 1, intermediate step 2, all the way up to intermediate step n. And those states still use that same state transition function that we define for a standard RNN. Little bit of magic to make that happen. In this paper, the state transition function is exactly the same whether we're coming from a previous time step or we're advancing an intermediate step inside the same time step. There is one little modification in that we're appending a single binary flag to the input vector that tells us whether this is the start of an intermediate sequence or we're somewhere in the middle of an intermediate sequence. Just a little hint to the network to know if it should be considering from a previous time step or let it know we're still spinning at the same time step. Okay, so if we treat this state transition as a standard state transition operation, it's going to work on the previous state, just like any other state transition. Previous state at the beginning is the output state from the last time step. Previous state for any other intermediate value is just the state from the previous intermediate value, walking up the chain. And then we need to arrive at an output state. A recurrent neural network at the end of every time step requires state to transmit on. And we're doing that by a weighted linear combination of all the intermediate states. And in fact, I haven't defined what this P is, which I'll get to in a moment, but this P forms a distribution. So this looks very much like attention over all of these intermediate states. Yeah, I think I got everything there. Same slide, different formulas. Along the left side, you'll see that we have something that looks very similar for outputs. We're doing exactly the same thing. From each intermediate state, we're using this weight matrix times the state value plus some bias vector to produce an intermediate output, yt1, yt2, all the way up to ytn. Of note, and this is very important, we're sharing parameters here. As we get deeper, as we have more and more intermediate steps, we're not creating additional parameters for the network because we're reusing this wy weight vector at every intermediate step. You'll see that we come up with the final output for the network in a very similar way as we came up with the final output state for this time step, which is just this weighted linear combination over all the intermediate outputs. Uses the same weights, form that same probability vector. Looks very much like attention.
A quick question.
Yeah.
I'm not sure if I picked myself up, so please repeat my question.
Okay.
So S's are the same. They're shared across the time steps. Is that
Yeah.
right?
So the question was, are S's the same? Are they shared across the time steps? By S, I'm going to assume you're referring to script S, which is the state transition function.
I'm referring to the S weight matrix, so between the intermediate steps.
These here?
Big S, yes.
So that's not exactly a parameter. That's a state transition function. That's your LSTM and all the associated formulas and parameters that go with it. So S contains parameters, but it's more than just parameters. It's an entire function for how to perform a state transition.
Now, y sub t is the sum of the y p's, but you have an arrow coming out of h. The same thing with s.
Yeah, so good catch. The question was, if y sub t is a linear combination of all these intermediate y sub t's, why is there also an arrow coming out of the h's, and the same thing for the output state st? That's a good catch. When I talk about this term here, pt, the weights that apply to this linear combination, those pt's are derived from ht. Those h's, as a spoiler, not much of a spoiler, they're called halting units, and they're information from the network about whether we should proceed with computation. Hey, look, and we're going to find them right now. So the column on the right, very much like the output y column on the left, little bit different in flavor. First of all, you'll notice that we still have these shared parameters, WH, going up the right, so these parameters are the same no matter what intermediate step you're at. And it's still the standard matrix times the state vector plus some bias. But we've also wrapped it in a logistic sigmoid. And that's because we need these to be scaled somewhere between 0 and 1. These are going to form a distribution that eat up some amount of our computation budget. You'll see that we have this P defined here. P is almost always going to be equal to, P at some intermediate step n is almost always going to be equal to H at some intermediate step n. The only case where that's not true is if we're done. If the step number we're on is equal to the final step, and we'll talk about that in a second, then this P, instead of this H value, should just be whatever computation budget remains. If your total computation budget going in is equal to 1, and you've already used up 0.9 of it, then the last intermediate halting probability is not going to be the value of this H intermediate unit. It's just going to be whatever's left. How do we know when we're done? Well, you can see here, this n, this tells us how many how many intermediate steps we're going to perform at any time step. And we do that by just adding up all of the values of the halting units until the values of the halting units are greater than equal to 1 minus some small epsilon. So once we've consumed all of our budget. We haven't left it as 1. We've had it as 1 minus epsilon for a corner case to make sure that it is possible for the network to only take one step at a given one intermediate step at a given time step. If we had not had the epsilon here, if we just said wait until all the h of t's sum up to greater than or equal to 1, because we're applying logistic sigmoid to the halting function, that's asymptotically going to approach 1, but it's never going to get there barring numeric instability, which I never want to rely on as a good thing for my network. That would force us to always take at least 2 intermediate steps at every time step. So this epsilon parameter just gives us the opportunity to take 1 step when we are close to 1. And this R, I haven't defined it rigorously up there, but this just corresponds to that remainder I talked about. All the remaining computation for this time step. And just some other names for these. So these H's are the halting units. These P's are the halting probabilities because they look very much like a probability distribution and they can be interpreted as the probability of halting. N of T is the depth, the number of intermediate steps we're going to take at time step T. And R of T is just the remainder. After taking N of T minus 1 steps at time step T, how much budget remains. So now we've defined everything in the S column. We know how to transmit state both horizontally across time and vertically through these intermediate steps in one time step. We know the same thing for Y. We know the same thing for H. And we know how to use the intermediate values to create the final values for any time step. This still looks very much like that unrolled standard RNN we saw a few minutes ago. If you just kind of ignore the complicated bit in the middle, we still have input, we still have internal state, and we still have output, and we know how to compute all those. So to summarize, this algorithm, which is surprisingly intuitive and simple, it really kind of caught me with how easy it was to conceptualize, is expand every time step to contain n intermediate steps. So at every time step, you're going to compute an intermediate state S, intermediate output Y, halting probability H. We're going to continue computing intermediate values until we consume our computation budget. Then we're going to compute the final state and output values as a weighted sum using the halting probabilities over those intermediate values. Great, we're done. I'm sure there are no more details to talk about. So now we have a mechanism that lets us pause and consider, lets us ponder for some variable number of steps at every time step. But what's the cost? We already know that cost is important because RNNs are expensive. Well, for a standard recurrent neural network, the cost is on the order of C, which is the cost of the non-recurrent components in the network, and then the length of the sequence times R, being the cost of the recurrent components in the network. Usually, this recurrent term, the length of the sequence times R, is going to dominate this C term, unless the C term is something like a huge softmax at the end for a massive vocabulary. For the most part, I'm just going to ignore this C and say the cost of one of these RNNs is sequence length times recurrent component cost. Well, now we've applied ACT. The cost of the network becomes that C term plus the sequence length times the cost of the recurrent components times the mean number of steps at every time step. So if the mean number of steps is 2, I've essentially doubled the number of the cost of my network. If the mean number of steps is 10, that's not great. It gets real expensive real quick. Mean n, but how many is that? How do I know ahead of time, or how do I help control how many steps my network is going to take at every time step? And this is a real familiar diagram, real familiar formulas. All I've changed is this little blob of text in the bottom right, so you don't have to spend time absorbing it all again. So this network, as it is, as I described it, it's incentivized to make these halting unit contributions very, very small, very, very close to 0. It adopts a tactic that I adopt in my personal life, which is if I delay decisions, if I just spend a lot of time thinking, I can never be penalized for making the wrong decision. This network is incentivized to make those halting units approach 0 so that it can spin for a very, very long time on every time step, almost down to the point of numeric instability, and never have to take a penalty for being wrong. That's not really what we're after, though. That's a super degenerate case for something that we're trying to get a benefit out of. So we need to penalize the network for long ponder sequences. I don't want to completely rule them out. I want long ponder sequences to happen where necessary. If there's a lot of information to be had at a given token, if there's a lot of pondering to do, I don't want to completely stop that from happening. So I'm going to define this ponder sequence for every time step t. And all that's going to do is it's going to add up the number of time steps at that, or the number of intermediate steps at that time step, with the remainder at that time step. And as a reminder, the remainder is just how much budget was left at the last step. So if the last step is very, very large, you're still going to pay a cost for having a whole bunch of really short time steps in front of it. The ponder cost for the network is just all this ponder sequence summed up over your sequence length. So this ponder cost is going to be the total number of time steps, the total number of intermediate steps the network took, plus the remainder at every time step. Now that remainder term looks a little bit awkward in there. If I were doing this, I would think, why do I care about the remainder? Why don't I only care about how many intermediate steps the network took? The longer answer is, this n of t is essentially a constant. It causes some problems computing the gradient. We're not going to talk about the gradients here. It's sort of a sidebar to this talk. I do encourage everyone to read the paper to see why they chose n of t plus r of t for the ponder cost. There's an interesting discussion on it. But then when it comes to our final loss function, we're going to take the loss function we had before, and we're just going to add tau times this ponder cost. Okay, great, I've introduced something new. We didn't talk at all about tau yet. Tau is just some multiplier, some penalty term on this ponder cost. And up front, I talked about one of the disadvantages being that we're adding a parameter, or a hyperparameter, to the network that it's difficult to set in a principled fashion. There is a discussion in the paper on how you can set tau, but it leaves the really hard question for future work. To set tau effectively, you need to be able to quantify for your particular problem how you're going to balance improvement of error, how much do you care about loss, versus how much do you care about computation time. You might be able to measure that and say, oh, computation time additionally costs me about this much per extra intermediate step. I'm paying AWS infrastructure, cost me so much. Here's how much I care about error. That's sort of a longer, deeper discussion we're not going to talk about here today. We're going to assume that tau is just a free parameter we can set. So early on in the training regime, the network is still learning how to use those halting units, those halting neurons. It will fairly quickly learn how to use them, but it's advantageous early on to heavily penalize additional ponder, to penalize tau. That just lets the network take some shorter time early on to ponder while it's still figuring out all its internal nuts and bolts. It's also beneficial to put a hard cap on the number of intermediate steps, just to keep us from running into any of those degenerate edge cases where we're going to run 1,000 or 1,000,000 intermediate steps. For all the experiments in this paper, a hard cap was put on the number of intermediate steps of 100. And in no case, after some initial sort of learning period of the network, did the ponder even come close to approaching 100. So the network does learn that it is not a valuable thing to ponder for that long. But we just have to modify the formula for n of t to include this constant m. That's just our ceiling on how many ponder steps it's possible to take. And the last thing I want to talk about for describing the algorithm is the paper takes a mean field approach to how it computes the halting probability, the value of the outputs, the states that get carried from time step to time step. It's also possible to take a stochastic view of it. We called it the halting probability for a reason, because it very much resembles a probability distribution. And in fact, what if instead of taking the mean field approach and doing the attention over and doing a weighted sum, what if at every time step I just treated that halting unit, that halting probability, as sampling from a Bernoulli distribution? That'll tell me stochastically when to stop, and then I'm just going to set my time step final state to be the most recent intermediate state and do the same thing for output. So Alex talks about this in the paper. He considers it unnecessary. He talks about some reasons why. I'm going to refer you to the paper for that discussion. I found it super interesting, but it's more involved than I can do justice for to standing up here and talking. And with that, I don't know if we're still going to do a break based on being a little bit behind, but we are? Okay, so we're going to take a little break. That's the algorithm. Digest it, think about it. And when we come back, we'll talk about some of the experiments and results that this paper took a look at, and then some discussion points that I had questions, and I know that my facilitators had questions as well. Thanks. Okay. I apologize if I'm a little bit hard to hear today. I've been unwell for a little while, so I've got my pharmacy here. If you need me to speak up, let me know. But I'll try and get through it without coughing too much. So before the break, we talked about the algorithm, described how it works. I found it an incredibly intuitive, attractive paper for how the algorithm fits nicely into any standard RNN structure. And now we're going to talk about some of the experiments and results. So this paper evaluates ACT on 4 synthetic tasks and then 1 real-world task. It compares an RNN without ACT to RNN with ACTs, different parameter settings for ACT. Of note, for all the synthetic tasks, it was a very basic RNN. It wasn't an LSTM or a GRU. One thing that I really enjoy about Alex's papers is that it's not about beating benchmarks. It tries to look at fundamental properties of the techniques and algorithms that he describes. So here, we're not going to be trying to set benchmarks. We're going to be looking at how ACT enables a basic RNN to tackle these tasks. And having said that, I'm not actually going to show you all 4 tasks because the results for all of them are essentially the same. They all broadly show the same outcome, which is that a basic RNN which solves the problem poorly or not at all will solve the problem well when you apply ACT. And we'll go through some examples that shows how some of the parameters matter, but we're not going to go through every task because it would be going through the same thing 4 times. I did want to describe the 4 tasks, though. Binary sequence parity. How many ones, how many zeros, what's the parity of a variable length binary sequence? Sequential application of logic functions. Given a whole bunch of logic functions in a pool from which to pull, can the network learn to apply those functions to some sequence of input bits? Variable length sequential addition. We have a whole bunch of binary encoded numbers, some variable length of sequence length of them, and it's going to do rolling addition. And sorting. Can it sort a variable length list of numbers? Now those are all fairly straightforward basic tasks. We know that we have other tools to accomplish them. But basic vanilla RNNs do pretty poorly at all 4 of these tasks. So we're going to show how ACT enables those to work. And one of the things that you see in all of the experiments is this graph on top, which just talks about what was the error rate versus the time penalty tau. This is to explore what the effect that hyperparameter tau has on the functioning of an RNN with ACT. And you can see here at the far right, we have this black bar. That black bar is the performance of the network without ACT. And in this case, the error is about 37, 38%. I call that a pretty bad failure. And you can see that as we vary that tau parameter from 0.1, being a fairly aggressive setting of the parameter, it relatively smoothly reduces the error as you reduce the value of that tau parameter. What this is telling me is that as you give the network more time to ponder, as you penalize its pondering less, it'll spend more time pondering, and that ponder time is useful. It's letting a basic network learn a task that a basic RNN was unable to do. You can see here at the bottom left, we have a whole bunch of curves that are the error rate over training iterations. And the colors of these curves correspond with what you see here. You can see a nice, pretty descending rainbow up at the top. You see that black curve. It's fairly red going down to blue at the bottom. What that's showing us is that networks which have a lower ponder penalty will converge to a much lower overall error rate, and they will learn more quickly. And then we also see this standard graph over here, which looks at not tau, but what is that mean ponder time? How much time are these networks actually spending on average pondering? And you can see that as you start to spend even a little bit of time pondering, I know it's a little bit small, probably a little hard to see, but it doesn't take much. As the mean ponder time approaches 1.5, meaning that as you're on average spending 1 additional ponder step every 2 time steps, the error rate drops dramatically and continues to drop. There's not a whole lot of benefit to ponder time past about 3. the network will take that time if you allow it to. So if you set tau low enough, it will take that ponder time, which will add cost to your network, but without giving you any appreciable benefit in terms of performance.
Sorry.
Yeah.
Is that the error on the training set, or?
This is test set error.
Sorry, can you repeat the question?
The question was, is that error on the training set? This is test set error. Yeah.
Was a sort of diminishing benefits after average of 3 ponder time generic across the tasks?
So the question was the diminishing benefits of about 3 ponder time consistent across the tasks? Broadly, no. Every task was a little bit unique. We saw that every task, the tau curve looked a little bit different. The ponder time benefit looked a little bit different. What that was trying to show us, or what that was showing us, is that there's no generally appropriate value for tau that's always going to work. It really is problem specific and difficult to set in a principled manner. A couple more graphs that are common to pretty much all of the synthetic tasks in the paper. And these ones give us a little bit of a hint towards some of the research that Alex was going to do after this paper. The bottom of this, the x-axis, is called difficulty. And difficulty is something that's easy to set on synthetic tasks. Difficulty in this case just corresponded to the sequence length. How long was the sequence being presented to the network? But this hooks up nicely with some of his later research around curriculum learning, showing that it is useful for networks to learn in a very controlled, staged fashion. That you start off training a network just like you would start off teaching a child simple things and then proceed to more complex things and more complex things. It's beneficial not to start at the most complicated example. But in this case, we're comparing the difficulty of the task to the time spent pondering or to the sequence error rate, again, for all of these different values of tau. We can see on the left that the amount of time we spend pondering, it's fairly linear. It doesn't start to explode too much until we get to some extremely small values of tau. When that happens, as the sequences get more difficult, the amount of time we spend pondering goes way, way up. You can see that for these 4 or 5 most permissive tau settings, when the sequences get long, that mean ponder time goes up to 8, 10, 12, 14 for this parity problem. We saw that for this parity problem, we're not getting massive benefits to letting the system ponder that long. So this represents to me that if you set the value of tau too small, you can still get good results, but you're going to waste a lot of computation on long sequences. And then this one just measures difficulty against the error rate, and it shows exactly what you'd expect to, which is that as sequences get more difficult, the error rate's going to go up, but as the tau parameter gets more permissive, you're going to do better on long sequences because you can spend more time thinking and pondering.
Just a quick clarification question. Yep. So the vertical axis, that's time steps, right?
On this slide here?
Yes.
The vertical axis on this slide, do you mean the y-axis or do you mean the stacked curves?
On the ponder side.
On the ponder side. The ponder side is the mean number of of intermediate steps taken at every time step.
Gotcha.
So you're going to see a variant of these curves with just some different values for all 4 of the synthetic experiments because they essentially show the same thing. Ponder increases the expense. You do get better results. It enables a very, very basic RNN to perform a task that it couldn't do otherwise. But let's talk about the one real-world task that was attempted. And this one is a Wikipedia character prediction task. This task is just given 500 characters of a Wikipedia article. Every character, predict what character is going to come next. This is a real-world task. It was pulled from a fairly standard data set. I didn't write down which one it is, but it's referenced in the paper. And on this one, I was a little bit saddened to see that adding ACT didn't really help all that much. It helped a little. You can see if you look at this on the right, bits per character here corresponds to the loss. Ponder corresponds to the mean ponder time. This black line is the average, or this black dot right there with this dotted line is the average of 20 runs without ACT. and it looks like it's about 1.58, 1.59 bits of loss. And for the most part, as you apply ACT with different settings of tau, you get a little bit better. There's a few there's more than a few cases that ended above. There's the great mass of the examples ended up doing better on that loss metric, but it's not a huge improvement. And I'm not convinced that by itself that would justify using ACT for this problem, if all we cared about was the error. But delving into where the network is choosing to spend its ponder time, that additional computation, it's interesting, and it gives me more questions than answers. It makes me want to go home and implement this and figure out what's going on.
Okay,
have a
yeah, I'm
question?
gonna be that guy again. Yeah. So you seem to have two modes over there. Is that correct? And do they correspond to something that I'm not?
Sorry, I didn't catch the question.
You seem to have two modes of data.
So the question is, there seems to be two modes of data. I'm sorry, I should have mentioned that. On all of the charts, graphs that I've shown thus far, you'll see that there are some things that are dark and solid and some things that are faint. The dark solid ones represent the average of 20 trials at that setting. So you can see that there are some dark dots with circles around them. That represents the mean, and in fact, along each of these axes, the loss and the ponder time, the variance that they saw at over 20 trials at this setting of tau. And that over 20 trial paradigm is consistent across all the other charts I showed. Yeah.
During our pre-discussion, I was wondering, would something taking a longer ponder time indicate maybe outliers in data? You know, you're kind of puzzled or stumped. It could be a more difficult like problem, like the longer sequence, but maybe it's also like an outlier.
So the question is, oh, you heard the question? Okay. Outliers isn't something I considered. However, with respect to needing more time to think, complicated examples, you'll see that more time is spent on tokens where there is high entropy, meaning there's a lot of confusion, a lot of additional information would be needed to say what comes next. If an outlier is a point of high entropy, high confusion, where additional information is needed, then that would be completely fair to say. Yeah.
Isn't that by definition, like almost, not exactly definition, but isn't that like a characteristic of all outliers though? It's something that doesn't make sense with the rest of your pattern.
That's a good point. If your definition of an outlier is, and it makes total sense, if your definition of an outlier is something that doesn't make sense, that doesn't fit the pattern, then yes, there would be high confusion there would be high entropy there, and that would elicit from this technique more ponder time. I take your point. And I find these fascinating. I can stare at these for ages trying to really capture what's going on. But what we're looking at is the same sequence of tokens from the Wikipedia dataset repeated 3 times. On top is the number of bits of entropy at every point in that sequence. In the middle is the loss function from the network at every point in that sequence. And at the bottom is the mean ponder time over those 20 trials at every point in that sequence. And if you'll take a look, you'll see that the ponder time lines up pretty well, not completely, but pretty well, with high loss and high entropy. Meaning that where there's confusion, where we're not sure, that's where more ponder time is being spent. Now, the ponder time you're looking at there, and that graph at the bottom, it's a little bit sparser. It's less noisy than either of the other 2 graphs.
Excuse me, isn't it the case that it's not necessarily corresponding to high losses or high entropy rather than the changes in the loss and entropy?
So, did we get the question? So, it is possible that it corresponds to changes rather than high entropy. Alex talks a little bit in the paper about it being only somewhat related to loss or entropy. Instead, it's finding critical points of change in a sequence. And you'll notice that those points tend to correspond to spaces between words. That's where there's a lot of potential confusion about what word might come next. But as soon as we can see the first character of the next word, things start to settle down. We no longer need to think as much. It's at least a little bit clearer what might come next. It corresponds even more heavily to punctuation. You'll notice at a comma, or especially at a period, those breaks in prose, those breaks in thought where it's time to start a new thought or start a new maybe sub-thought in your sequence, the network is spending even more time pondering. I find that fascinating. I find it frustrating that that doesn't correspond to more improvement in the lost results on this task.
May I ask a question?
Yeah.
If theoretically, if you had all the computational cost in the world, if you paid more attention to every single word, would it hurt performance? So if you paid more attention to a word that didn't need attention in the first place, would it hurt performance?
Short answer is I don't know.
Okay.
If I had to guess, I would say there is not any kind of significant advantage to spending a lot of ponder time on very sort of low information, low entropy, easy tokens. I would say that it is already spending additional ponder time where it is valuable to do so, but the mere act of spending additional ponder time may not yield a lot of extra information about what's coming next, about how we reduce the loss. This is the same task, but with the XML tags left in. So this text now gets really messy and dirty, and I find this one really interesting as well. Same three graphs, top to bottom, different string of text. And you'll notice right at the beginning, very beginning of the sequence, lots of ponder time. It's thinking for a long time because it has no information. This is the beginning of the sequence, doesn't know what's happening. There's a very small bump between United and States because those two words are often going to come together. We see some bumps at the first space after every word. But where I'm very interested in is where it hits the XML tags. It clearly has learned that the open tag, the open XML bracket, is interesting. Something's going to happen. It's worth thinking about what's going to happen. What's even more interesting is that the very largest ponder time was spent when it hit this first XML tag. And you'll notice that because of the characters chosen, it doesn't actually get to see the open tag. It doesn't get to see the open tag for this title section, which means that it recognizes that it's time to have an XML tag that is an instruction or that's a section, but it's never seen one before in its context, in its history, so it has to spend a lot of time thinking about what this might be. And the next character is a slash, just indicating, okay, great, it's time to close this tag, close this section. And as soon as it sees that close, it stops thinking anymore. It says, I don't know what section I'm in, but I have no way of figuring that out from the information I have, so let's just see how we proceed. Let's just have error. And you can see that every time there's an open tag. Every time there's an open tag, it considers, except when it's time to close that open tag. So it certainly recognizes that balanced sequence of open, close, open, close. I don't know what that tells us about performance, but I found that really interesting. So that's the end of the experiments and results in the paper. I found that a little bit frustrating because I wanted to know more. But it left me thinking, and I had some questions, and I know that my facilitators had some questions too. So for the discussion section, there's a couple of things we know we want to talk about, and I know there's going to be a lot of things that you want to talk about, and we're happy to at least try and answer the questions. No promises we'll know the answer, but we'll try. Yeah.
Just one thing before you start. How was the entropy calculated? Did he just take did he just take the probability of the next character multiplied by the log probability?
Yeah, that's exactly how.
Can you repeat the question?
It was how the entropy was calculated. It was just the log likelihood of the next character.
What was the first data set that we got a better result? You show like two data sets, I guess.
Oh, so there's actually 4 data sets, or 5 data sets. The first 4 were synthetic tasks, being those 4 synthetic tasks, binary sequence parity, logic functions, addition and sorting. On all of those, ACT drastically outperformed a basic network. On this real-world task, the Wikipedia next character prediction, which used LSTMs rather than basic RNNs, we saw minimal improvement. Yeah.
So is it safe to say that, for example, in the last graph or example, once you open the XML tag, is it safe to say that every time after the first time it reduces the pondering time?
The question related to the XML tags, and is it safe to say that every time it encounters a tag or an open after the first time, that it reduces the ponder time? I don't think it's safe to say that. We have very short sequences here. In particular, this example doesn't show us any effective nesting. It doesn't show us how this revision tag might get closed somewhere over here. And the ID tag is within the revision tag, and is it able to have that stack internally? So I don't think it's safe to say that every time it's going to reduce the ponder. Did you guys have thoughts beyond that, or?
Maybe I can come back to a slightly different point, because I don't think I can answer that. But I just noticed, looking at this graph now, that the opening to the title corresponds to 0 loss and 0 entropy. If you look up, so someone whom I have not seen has asked the question if the changes to the entropy correspond to jumps in ponder time. So that is an argument for that point of view. But if you see, I'm closer than you guys, so I can tell you that the ponder times for ID, revision, and another ID are exactly the same height, plus or minus.
I didn't notice that. Thank you. Yeah.
From an engineering perspective, does decreasing the penalty tau significantly increases the training time to converge?
So the question was, okay, so the question, I'm going to repeat the question anyways. Does reducing the parameter tau significantly increase the training time?
Yeah, to converge, because RNN is, well, you know, very hard to converge.
RNN, yeah. So I think that's probably best illustrated by this graph here in the bottom left. I know it's hard to see in the back. I'm sorry for that. These graphs are a little small on the screen. You can see that as you decrease tau, which corresponds to moving down to the lower lines, the light-colored lines on this graph, you can see that the network does converge both to a lower error rate as well as converges more in a far fewer number of iterations. What this graph doesn't capture is the additional computation cost spent pondering. And you can see that as these dots turn bluer or purpler, we are spending significantly more time pondering, to a degree where if you look at the furthest one off to the furthest combination of trials off to the right, the variance is huge. The variance goes between 4 and 8.5 ponder time. That ponder time is essentially a linear multiplier on the cost of that neural network. Making a neural network 4 or 6 or 8 times more expensive is only worth it if you converge to a much lower error rate, or you converge 4 or 6 or 8 times more quickly. But there's no, or at least not in this paper, there's not a principled mechanism linking tau with ponder time with cost, because that's a difficult thing to do. So it was left for future work.
I have 3 questions queued from online. So one question is about the tau. How do you think about the idea of adjusting tau by taking the derivative of the error rate with respect to the computation budget?
I don't know. On the spot, that's not something that I feel I can give a good answer to. I need to think about that one. Either of you guys have thoughts about that, or?
So the total loss is linear in tau. Can you say again how you would like to To compute tau by taking the derivative? Can you repeat the question?
The question is, how about adjusting tau by taking the derivative of the error rate with respect to the computational budget?
Right.
Yeah, so the loss term with respect to the budget, you want to compute tau based on that. Right, it's tau times the budget.
Yes.
Yeah, so you take, if instead of having tau multiplied by the budget, what if you just take the derivative of the error with respect to the budget instead of having tau as a multiplier? I think that's the question.
I think that's a more complicated question than I'm prepared to commit to up front here. I am going to go home and think about it, though.
Okay, how about a simple one? Is there code available?
There is an implementation available for ACT. It is not from Alex Graves, but it is a well-downloaded, starred, and forked GitHub repo. I included the link when I sent out.
Should be on our website.
Look on the website.
Okay, I'll update it. Okay.
Yeah.
Okay, sorry, one last question. Also from the same person, Coding with Pedro. How does ACT compare against LSTM and GRUs?
So the question is, how do ACT compare against LSTM and GRU? It's not a comparison. ACT is a generic technique that can be applied to any of the standard model recurrent neural networks, including LSTMs and GRUs. In fact, I would think that you'll get the biggest benefits from applying it to a model more complicated than the very, very simple RNN model, because the very simple RNN model is a toy these days. It doesn't really get used for practical tasks.
So the experiments that you showed us, are you picking?
So the experiments that you showed us, was it against, you compared it against vanilla RNNs?
Those were vanilla RNNs in the synthetic experiments. They were not LSTMs or GRUs. This is a complementary technique to LSTMs, GRUs, or any other standard form of recurrent neural network.
Do you think there is some competition going on if we actually apply it to LSTMs? Some competition will be going on between these pondering pondering method and the gates at the LSTM, because there is some overlap in the functions, as I would see.
So
I guess for the Wikipedia one, they use LSTM for most of them.
for the Wikipedia one, it is using an LSTM.
And still
Sorry, it's
Slightly, not that much.
And it's still improving.
it
Slightly.
It only improved the loss on the Wikipedia task slightly using an LSTM with ACT. I had hoped to see more, and I still have many questions about when you might see more or less.
Even for sorting is LSTM. So they were using RNN and LSTM, both of them, to see if they can actually improve the system, not just RNN. If you even replace the RNN cell with LSTM, will it actually improve it or not? For sorting, they will improve it. Mm-hmm. You will be able to improve that. For the Wikipedia, they couldn't manage to do anything. Mm-hmm. I mean, they didn't change it that much. But for the comparing LSTM with ACT, maybe it's a discussion for you. I don't know if we get to that.
This is essentially discussion questions now. We can.
But for me, it was like an interesting thing, because the whole thing of GRU and LSTM was like to be able to capture those long-term dependency, to be able to say the current input might not be that much important. I wanted to be able to look at far back in the sequence and I still keep them in the system to be able to use and produce some result. But here is kind of the other way around. It's like, yeah, history is important, but I want to put more pressure on the current input to be able to produce something for that current token. So it's like kind of the other way around. So it's kind of like a trade-off. It's like, are the current input is important or the history? So LSTM was looking at the history, ACT looking at maybe current input.
So there is no mechanism in LSTM that would stop it from emphasizing the current input and diminishing the information from the previous time steps. Like theoretically, there isn't a mechanism there, right?
For the LSTM?
Yeah.
There is. It's from the forget gate, right?
Well, you can't guarantee that that's gonna. You don't control
But
right?
you let it learn from the data.
So exactly. So, like, it could happen, and most likely it does happen. But I'm just saying that the gate, so like the input gate, can basically do a very similar thing as the pondering. That was the overlap that I saw, and I was wondering if this is a good avenue to explore. How can we make sure they work well together? Like if it's pondering already, do we actually need that much of an input?
This is similar to one of the discussion questions. I think it was Rohollah that posed it, which is, have we exacerbated the long-term dependency problem by increasing the depth? We already know that LSTMs, though in theory they have an unbounded horizon for the sequence, they can in theory remember information from an infinite amount of sequence ago. In practice, that's not the case. And the ability to remember long-term dependencies is pretty directly tied to how long ago they were. We've made these recurrent neural networks deeper. It looks similar to increasing the length of the sequence. And if the gold arrows you saw here were a standard recurrent model, LSTM, you would see the previous time step to the current time step to the next time step, and it would just flow through without considering any deeper layers. This red arrow is the part that ACT makes worse, makes deeper, might exacerbate the long-term dependency problem. I did have one thought as I was putting the slide together, was that we're not directly computing the output state from the end, or at least not in the mean field model. The mean field model, every intermediate state, including the first one that pulled directly from the previous time step, is making some contribution. So that lets the network at least provide some amount of input from a shallow point in this ponder sequence. We saw in practice that ponder sequences are usually short, 2 or 3. So at worst, it's making the long-term dependency problem 2 or 3 times worse, which sounds awful now that I say it out loud. But the network at least potentially has a mechanism to alleviate some of that.
Yeah, exactly. That's completely true. And the funny thing is, like, if you actually increase the pondering, so you're going to have more dependency in your current state, so you might be able to lose information from the history. And it's a discussion point because it's kind of my idea versus Alex Gray, which is not fair. But if you go back to the NLP task, here Alex claimed that the reason that the model is pondering here is because the model is actually thinking about what he should do for the next sentence or for next word. But my idea was, like, because there is also pondering going on here, the network is actually removing what he has learned so far, because when you're passing information through lots of layer of pondering, you're losing the history because it's a trade-off. And maybe after one, I don't know, the dot or the period, the network said, okay, I'm done with the previous sentence, I have to kind of start from scratch, kind of removing the history. Maybe the network is not actually thinking, is kind of trying to overriding the history. And that was my idea.
It might act as some kind of soft reset on the state.
Sounds like that.
Can you not verify that from that distribution that you talked about? Because you said from 1 to n there's a distribution that's learning probabilities, right?
I absolutely could.
So if the n probability is really high, then that's probably what it's doing.
And I think that would be a really interesting thing to verify.
Did you ever look at that in the graphs?
Pardon?
Did he make any graphs with?
He didn't make any graphs. There were no graphs in the paper that showed the distribution of ponder over sequence length, or the distribution of halting probability over sequence length.
Yeah, are you categorizing this method as a deterministic approach or undeterministic?
So the question was, is this approach deterministic or non-deterministic? In the, initialization aside, I would say that the formulation in the paper that takes the mean field approach is deterministic because it's not introducing any stochasticity. You could take a stochastic approach where you're sampling the halting probability from a Bernoulli distribution based on the value of the halting units, in which case it would be non-deterministic.
Could you kindly do a quick recap on the mean field?
So, if we look, for example, at the output neurons, the intermediate outputs on the left, you can see that, excuse me, the final output is this weighted linear combination, this attention. If these weights were all equal, this would look like essentially taking the average of all of those intermediate units. I know we haven't normalized by the count there, but it looks a great deal like taking the average. These probabilities are not equal. It's some distribution, so it's going to be a weighted combination. So we're going to get some combination of those intermediate values. If we took the other view of the network, the halting probability is being stochastic. We're going to sample a Bernoulli distribution at every intermediate step, and we're just going to use the last value, the last intermediate y value, or the last intermediate s value, as the value to move forward with for that time step. Then it would be non-deterministic. It would be stochastic. All right. Where was I? Too many slides. Oops.
One observation I found interesting was that in the two plots you showed of the Wikipedia, there was one case where there's high error but low pondering, and that's when it was the ID numbers, which are essentially random numbers for all intents and purposes. So it makes a lot of sense that's not thinking too much about things that would never be able to predict.
Yeah,
I think that's an impressive feature.
I saw Mersa's hand was up at the back.
I just wanted to ask in terms of application, considering ACT and attention mechanism, are any research showing which one has advantage in solving what kind of problem? If you want to design an architecture, should we just try both, or is there like a rule of thumb deciding which one would work better?
So I haven't seen ACT widely used in any system that was adopted later, despite the paper being reasonably well cited. I think my personal view is that the lack of emphasis on benchmarking against real-world tasks harmed its sort of adoption and uptake in future papers. I have a discussion point coming up about some times when I think that ACT has potential, some questions that I'd be interested in answering, but I don't have answers for you.
But it's computationally more expensive, I guess, so maybe that's also...
It is a computationally expensive technique, which is another deterrent to its uptake. Yeah.
Someone also asked about some related questions, so I'm trying to check my understanding. So based on what you said, my understanding is that ACT is somewhat orthogonal to attention, in a way.
Yeah, I would say that ACT is somewhat orthogonal to attention. It includes a mechanism that looks very much like attention. It's not exactly attention. It is a weighted linear combination, which looks very much like attention. So,
but that part is still within a very, very short range, right?
Yes.
Exactly. That does not extend to.
That doesn't extend.
So, is it fair to say that this is mostly about sort of a way of influencing the gradient to a certain direction, whereas attention is about like making shortcut of your input data?
There was a particular term that I think it was Alex used when we were discussing this paper, which was it looks very much like a variable depth RNN. It is a way of a meta technique that extends the property of an RNN that lets it deal with a variable length sequence and turn it orthogonal and let it deal with a variable length intensification on sort of a particular area, a particular token.
Just a comment on that. This is not a good, this variable depth would mean that the weights were not shared within depth layers. Because usually if you have multiple units stacked on top of each other in a deep RNN, multiple RNN cells on top of each other, the weights wouldn't be shared. Yeah. But here all the S's are the same. So it's not really variable depth.
Which captures the other discussion point we had, which is what happens if we don't share parameters? there are a couple of places that parameters are shared. These state transition operations that include some parameters, they're shared both between the time steps as well as vertically all the way up the stack. So it's going to be the same function with the same parameters. It certainly would be possible to, for example, remove the binary flag that tells it whether or not it's at the beginning of an intermediate sequence or not, and have this state transition function be parameterized differently than any in the stack. It would also be possible to take all the parameters in the stack and at every layer have a different set of parameters. You would, at that point, essentially have to have a hard cap so that you didn't have an infinite number of parameters. My intuition from reading the paper, looking at the results, is that there is little or no benefit to be gained from not sharing parameters, if only because there's nothing special about any particular depth that would, across all problems, indicate a certain different type of operation, different type of computation should be taken. Yeah.
I don't know whether it's correct or not, but my understanding is like this is different from attention, because in attention you try to, for example, get the importance of the previous sequence and then add it in. For example, when you are trying to do a translation or that sort of thing. But in here, I guess what it tries to do is that based on the current token that it's facing, it tries to find out the optimal, not the optimal, but somehow the optimal computational cost that it needs in order to, for example, decrease the entropy or that sort of thing. I guess it's like having this dynamic way of assigning the computational cost based on the entropy and the...
It is a dynamic way of assigning cost. I'm a little bit beginning to regret drawing the connection to attention. Other than the fact that the math looks very similar, I do think it is a little bit of a distinct mechanism from attention.
The state transitions, is there non-linearity in them, or?
There can be. The state transitions are any arbitrary function that you might encounter in the operation of a neural network. So for example, if these were an LSTM, the state transitions would include all of the gates as well as the next state from the current state modified by gates. So all of those parameters and operations are tied up inside this one script S operation.
So do you know, I'm just asking out of curiosity, do you know any paper that tried to combine this architecture with also the attention one? Because based on that you would have like, on each token you know how much computational cost you should put in order to get the best results, and also by attention you know how to look at the history. Is there any something like that, or
so
possible? Or?
A brief search on my part didn't turn up any significant papers that integrated this technique with other techniques, architectures. I cannot say that I've done an exhaustive survey. Did you guys find anything interesting, or?
I can tell you how you could implement this, well, how I think you can implement this with attention. So suppose you put a cap and unroll and then set all the sequences to repeat their tokens that many times. Then it would effectively, okay, with a single layer RNN, that would mean you are always pondering the maximum amount of time allowed. And then attention is always detracting from the input. It's setting some things to 0, more or less. So if you had an attention layer in there saying, I'm only allowed to look at the first n elements, or small n elements of my sequence within the sequence, right? Each token gets repeated many, many times. So I'm only allowed to look at the first n repetitions. You would effectively have something like this, where your attention layer could play the role of the ages. But that seems more intuitive to me than actual attention.
It is not immediately clear to me why we would do that versus this. I can see sort of the construct, but...
Well, it bridges the gap between an attention world and RNN world, but otherwise RNN is better for sequences. You don't have to pre-repeat everything 100 times.
Wasim, did you have a...
So he...
Okay. Is as just one layer?
Sorry, I didn't catch the question.
Is the network as just one layer?
Yes. S is one single a state transition operation. I don't want to use the word layer exactly there, because it could be any arbitrary operation that takes you from one state to another state. In all the standard constructs, S would be one application of the LSTM operations to transition state.
So S is convex?
There could be some kind of activation function in S that introduces nonlinearities.
Sorry, I mean the S between the ST to ST1 and ST2. That part, is it convex?
Don't entirely follow. It could certainly be nonlinear. You could have any standard activation function or several in there, which means that it's certainly not always the case that you could compose all these as a linear combination.
Should be convex, because you applied some like smooth functions to it, right? So it should be like sigmoid and
You certainly could apply logistic sigmoid, 10H, linear rectifier, whatever you wanted in there. This is an arbitrary operation.
For example, if it is ReLU, then in this case it's convex.
It could be sometimes.
But in that case, does that mean y is simply the fixed point of this convex function, which becomes irrelevant to the input? If this sequence goes arbitrarily deep, it will always converge to that fixed point, because the function is convex, and it becomes it becomes irrelevant to the input. It looks like a model collapse situation.
I mean, you could probably compose a state transition function where where you could have these YT always converge on a single fixed point. I'm not sure why.
Because the point of this paper is that if the depth, if the time of pondering goes arbitrarily high, that means you allow the computer to ponder on some place forever, then the accuracy could only increase.
In fact, some of the results before have shown that essentially pondering longer than 4 or 5 steps is usually not helping at all.
But it doesn't decrease the performance, right? Assuming you have all the computation resources.
Extrapolating from a graph with 6 points, yes, but the max was about 100, and you could technically, expecting that LSTM cell with hundreds of, probably thousands of parameters inside, or millions actually, with a few, with 6 or 7, or maybe even 100 ReLU applications would converge to a fixed point. I'm not sure that is.
So that's
but it's an interesting thing to check.
So basically, you think it's possible, it's just not tested in the paper, or the paper doesn't get anywhere close.
I think the loss function would effectively force the network not to go into that regime. The network wouldn't want to just get the same number all the way at the top. Unless...
One more thing, keep in mind this is a dynamical system, so every point where you have the power factor is greater than 1, you explode to infinity, and if it's less than 1, it goes to 0. So the notion of convexity that you have in mind doesn't quite apply here, because it is a dynamical system.
Can I suggest to move
Sorry.
the discussion?
Yeah, it's getting too long.
Well, these have been discussion points. This is the last discussion point we have up here. I'm happy to keep discussing it amongst the group. But this one is a little bit more of a qualitative question. Is it worth it? Is it worth, for a problem, the additional cost to get what might be a marginal improvement? I know that's a hard question to ask, given that a lot of things can change problem to problem, network to network. If we extrapolated from the one real-world example we saw, where we saw minimal improvement, is it worth it to include ACT in your expensive recurrent network to make it even more expensive? If I could extrapolate from that one data point, I'm only seeing minimal decrease in the loss function. Probably no. Might change with different problem types, different networks, different capacities. But there were a couple of things that made me pause, which is one of the things that I'm very interested in are recurrent neural networks with external memories. Lines up with some of the work that Alex has done, particularly around, he was one of the lead researchers on neural differential computers, neural Turing machines. They have an external memory as a key component of those architectures. This network, beyond letting you stop and ponder on a particular token of input, gives the network the opportunity to do multiple sequential queries to a memory. I find that a compelling idea. I'm a little bit surprised that I didn't see it in some of Alex's future work, where this type of technique gives you an opportunity to query that memory multiple times and apply your changing state context at the same input context to get multiple values, multiple associations back from that memory. I find that a really compelling idea, and if anything will get me to implement this paper and try it out, it's going to be that one. It's going to be asking and answering that question.
Can you elaborate a little bit on this external memory again? Sorry.
So an external memory is just a component that you can tack on to lots of types of recurrent neural network that will explicitly save the value of your state from some previous time step, and then can be retrieved later, either directly by a key, directly by a location key, indirectly by a content key, using your current state as a query to that memory to get some historical state back.
It's like applying a dynamic programming to this LSTM sort of.
Very much like dynamic programming. And then giving a network the opportunity on a single token where it needs to stop and ponder, but to sequentially query that memory some number of times, I find compelling. And then hard sequences. None of these tasks that the paper undertook answered my question about hard types of sequences, those prepositional phrase attachment or Winograd schemas. I know that there are hard sequences of language and non-language sequence tasks out there, and I don't feel like this paper addressed my question. So maybe the additional cost of ACT gives you benefits on very difficult or challenging types of sequences. But the short answer is I don't know, and I'm curious to find out.
I just have two things. First of all, what did he compare with only? Did he compare with a single layer RNN, or did he compare with a multi-layer RNN? Like, what was the benchmark against? Was it a single layer RNN?
For the synthetic tasks,
Yes.
It was a single layer RNN. I don't know what the architecture was for the real world task.
Single layer.
Yes. Okay. But when you have the ACT, in some places you show that the average was 3, the average was 4. Doesn't that mean that you would have wanted to benchmark a network that with, for example, an RNN that is 3 layers deep, for example? Like, don't you want to?
Perhaps, but that brings us back to our question about parameter sharing, because the parameters are the same no matter what the depth of this network, whereas you would be potentially adding additional parameters if you were to deepen a LSTM network, for example. You'll fix the parameters the same?
Yeah. So it's more of an apples comparison.
That's a fair question, but okay, you can't compare one model with single layer, the other one with multiple layer, because that is not fair.
Yeah.
But comparing like an ACT with one single layer of RNN, okay, you can say it's not fair. And the funny thing is, yes, the paper is well cited, and today I find another paper which the title was actually comparing fixed and ACT RNN. And they said if you actually have a fixed number of those, I don't know, dips layer, and having that one as a baseline, instead of just having RNN as a baseline, it's having an RNN with, let's say, 2 layer of dips, or 3 layer, or even they had like 8 layers. But for every single input, don't have anything fancy, and they just use a uniform distribution, and they kind of get the same result. And they said that, and the paper is like for just last year. So they said that's the better baseline, and they said that they could get, they kind of get the kind of same result just for using a fixed number of layer and using just uniform distribution.
So same with what? With ACT?
So
ACT and uniform?
So the ACT kind of using a variable layer of dips per input based on the input. It's kind of like attention based on the input and history. You decided that, oh, I have to ponder here. But if you say ponder, always ponder 2 times for every single input. Well, that's maybe the correct baseline for that paper. And they said if you actually do that, you will end up having the same result that Alex get in that paper.
Same with ACT, right?
Yes.
Okay.
So then my question, and I haven't read that paper, but my question then would be, if you get the same results, would you actually save computation by having ACT and allowing it to vary lower in some cases, and also make sure that it's a fair comparison with respect to parameters and parameter sharing? Yeah.
I was wondering if you would see the same patterns as you showed that you showed with regard to the character prediction task. I mean, I wonder if you'd see that because, like, without pondering being variable, I don't think you would, right?
No.
Theoretically.
Yeah, but they said, well, if you're going to get the same result.
This bottom graph only makes sense where the ponder is possible to be variable. And these two are just the losses that...
So I think it speaks to your point where you were saying, well, I hope it added more to the results than it did. So that's great to see. Like I can see internally it's doing the right thing in computation, but why is it not translating into better results? Sorry, I just wanted to emphasize that.
It's probably something to do with computational complexity, maybe. Maybe after a certain point, you don't need more computational complexity to boost. Like, for example, ACT cannot squeeze out more computational complexity out of the problem. Okay, and or all of a sudden, what it can represent is very limited. That's what my intuition tells me, at least when he showed me the Wikipedia results. But the other thing is he formulated this budget in a weird way. Like one thing, to me, it's natural to formulate the budget in a reinforcement learning setting.
I did have a thought around a reinforcement learning setting. To me, a reinforcement learning setting in some ways globalizes the budget. The budget here, these ponder sequences, we have some amount of ponder happening local to every time step. We could certainly formulate the problem in a reinforcement learning context where you're trying to minimize global ponder time, or global ponder time becomes a penalty. And then you have some external actor, some policy, which is assigning ponder time to the tokens as you go along, according to that global reward function. I see them as very similar, and I had a similar question, but I just see it as keeping the halting unit decision whether or not to continue pondering local versus making it more of a global decision.
Because then he wouldn't have to have the artificial cap on it, even though it was too high. I think it would have.
I think it's a very interesting idea because if you read the comment on mean field versus stochastic approach, he actually says that both sampling from Bernoulli and mean field approach tends to be dominated by the last term. When the network essentially says, oh, okay, I'm done. Make P large enough so that I just blow through my budget right away. Having a reinforcement learning approach could mean you have a more balanced sequence. You're actually using mean field and not the last element. But I don't know if that will actually help.
I have many similar questions. I think it's a great question. I don't know the answer, but I think it's totally reasonable to ask questions about reinforcement learning like formulation.
So maybe you can discuss that more after the session, but I think we'll wrap up. Are there any other remaining questions or discussion points? No? Okay. So let's thank our speaker and our panel.